So, we are talking about today some sample questions on the sample test. This is two particles of equal mass, one with charge E, right? The other with 2E. So, basically, it's just a positive charge, right? One is basically, okay, a single electron. It's missing a single electron. And this other particle over here must be missing 2 electrons. But they're of equal mass. Wow. Maybe their mass is different by 1 electron, but more or less maybe they have the same number of protons, in which case that extra electron is insignificant. Anyway, they're accelerated from rest by an electric field into a magnetic field. Okay? Compare their velocities upon entering the magnetic field and compare their radii of circular paths within the field. This is the magnetic field then, right? So if it's got a magnetic field, it's going to be having a circular path. Okay? We got to compare their velocities upon entering that magnetic field. So a quick diagram here. We have maybe a particle, 2 particles, and here it's either positive particles, and so they would have a positive plate here and maybe like a negative plate here with some kind of hole in it. Okay, and then over here we've got maybe some kind of magnetic field that's going down. Anyway, so they're in an electric field. They're accelerated here, and then they enter this magnetic field. All right. Now their charges are different. Their masses are the same. And so what's going to happen so we want to compare their velocities upon entering the magnetic field. So basically we know that the one with more charge will experience a larger push from this electric field, okay? And since they're the same mass, it must be that I imagine that when it gets here, it's going to have a greater velocity, okay? So let's go ahead and take a look at this. All right. So I'm going to call this guy charge Q, right? And I'll call this guy charge 2Q, right? So basically this is Q1 and this is 2Q1, which is actually equal to Q2. Oops, sorry. Q2. Q2 is twice that of Q1, right? So now in the electric field, basically we know that our change in electrical energy should be equal to the change in kinetic energy. Okay? And so we know that it's a delta V Q, right, is equal to 1/2 mv squared. Okay, now it says that it's 2 particles of equal masses accelerated by an electric field, right? So we could put this in terms of the electric field, right? But in the end, remember that delta V over R is equal to the electric field, right? And so in the end, we have the same electric field, we have the same delta V. So I'm just going to go ahead and not even introduce the field. And I'm just going to say that, look, these 2 particles, Q, are going through the same potential difference, all right, without necessarily introducing the idea of the electric field, because in the end, the potential difference is dependent on the plate separation and, the field strength here. So I'm just going to leave it as a delta V. Excuse me. So now, basically, what I'm going to do here is I'm going to take this equation and I'm going to build it for both particles, right? So I've got delta V Q1 is equal to 1/2 mv1 squared. Then I've got delta V Q2 is equal to 1/2 mv2 squared. All right. And now we want to compare their velocities. And so I'm going to go ahead and solve for their velocities in these equations here. Okay. And so I'll just solve for it in this one. So I'll multiply by 2, I'll divide by mass, and then I'll square root it. So I'm going to get a delta V Q1 times 2 over mass rooted is my velocity 1. And the same thing goes over here, okay? Delta V Q2 over M rooted is equal to V2. But don't forget, we've got this relationship up here that Q2 is 2 times Q1, okay? And so basically, I'm going to get rid of Q2 here and replace it with 2 times Q1. So this is basically going to end up being 2 delta V 2 Q1 over M is my velocity of my second particle. Okay. And over here, I've got the velocity of my first particle. All right. Now I'm going to keep those two equations for part 2, but I also want to make a comparison. So when you make a comparison of these things, you're going to want to basically kind of state which one is greater and by how much. And so what you do is you tend to do V2 over V1. All right. Perhaps I'll do this in red. So I'll take V2 over V1. And I'll basically just take, okay, the square root of 2. Well, actually, if I'm taking V2, this 2 and this 2 becomes a 4, right? Square root of 4 over delta V Q1 over M over the square root of 2 delta V Q1 over M. All right. And if you look closely at this formula here, I can essentially pull the numbers out, and I'm going to say, well, this happens to be the square root of 4 times the square root of delta V Q1 over M. And this happens to be the square root of 2 times the square root of delta V Q1 over M. And so the delta V over Q1 over M cancels. And basically the ratio or the difference or the comparison results in the square root of 4 over the square root of 2, which is just 2 over the root 2, which is actually just, in the end, square root of 2. Right? Is that right? Yeah. I'm going to take a square root of 2. Yeah, like that. Yeah, that's how we do that. Pretty cool, huh? And there it is. So that's the answer to part A, is that V2 equals V1. Sorry, I said that wrong. It's V2 over V1 is equal to the square root of 2, implying that if I multiply, if I write this like this, I'm going to write the square root of 2 times V1. So basically, we say that the V2 equals the square root of 2 times V1. So V2 is greater because I have to take V1 and multiply by root 2 to get V2. So this, remember what I said at the beginning, that the velocity of the more charged particle is going to be greater. And by how much? Well, we don't know the actual velocity, but we do know by what factor it will be greater, okay? And so we have all of that information here. The reason why we can't figure out the exact velocities because we have no idea what the potential difference is. We have no clue what the mass is. And so in the end, but we know That's all. So that's all we can find out. All right. So now in part B, we're basically now, instead, we're going to be comparing the magnetic fields, and we want to compare the radius of curvature. So remember, for force magnetic is equal to QVB sine theta, okay? And I'm going to go ahead and just make the assumption that this is going in at 90 degrees, okay? Or it doesn't even matter what angle it's going in, because in the end, this sine theta is going to cancel because it's going into the same field. And so this sine theta will just always be the same for both particles, right? Matter of fact, maybe I'll leave this in here, and then you'll see that it actually doesn't matter what angle it is. Just kind of like it doesn't matter what strength the field is, and it doesn't actually matter. Well, what else doesn't matter? Well, that's all that's over here. The charge does matter. The velocity actually does matter. All right, so now, basically what I'm going to do is I'm going to say, all right, remember that the force magnetic is always equal to the centripetal force, okay, on the particle. Because when a particle is moving in a magnetic field, it travels in a circular path, okay? And circular paths follow the rules of centripetal motion. And so this is just going to be force magnetic is MA C, but remember AC is just V squared over R here. All right, so I'm going to go ahead and replace my centripetal acceleration with a V squared over R. V squared over R is equal to QVB sine theta. Okay, and so this is now going to be my equation. So what I'm going to do is I'm going to do the same thing I did over here. I'm going to build an equation for the first particle, an equation for the second particle, and I want to compare their radii. So I want to go ahead and solve for the radius. This time I actually think I'll solve for the radius first. Here I did an extra step. I made the two equations and then solved for V. So now I'm going to go ahead and solve for R and then make the two equations. It'll actually save me writing down one thing, right? So if I solve for R, I'm going to get this, mv squared over qvb sine theta equals R. That's just algebra there. And look at what happens here is I'm going to have a V cancel. And so in the end, I'm going to get with my R, my radius of curvature, is mv over qb sine theta. Okay? And this is valid for each of the two particles. Okay? For each of the two particles. And so if I take a look at this here, I'm going to make a equation for each of the two particles. And I'm going to say R, the radius of curvature of the first particle, is equal to mass V1 over Q1 B sine theta. All right. And the radius of curvature of the second particle is mass V2 over Q2 B sine theta. So you might be asking, why did I decide to make subscripts on the V's and the Q's, but not the M's, for example? Well, because remember, the masses are the same. So if I put a subscript of 1 here and a subscript of 2 there, then in the end, I'm just going to have to later on change them to the same thing, because remember, the masses are the same. Same goes for the magnetic field. The magnetic field is the same. So there's no reason to say that R1 went into B1 and R2 went into B2, because they both just went into B, okay? And then again, the same thing goes for the sine of theta, right? So theta 1 and theta 2, but I am putting a 1 and a 2 here, because remember, their velocities in the magnetic fields are different. Remember, one velocity is this, and V1 is this, and V2 is this, right? And also their charges are different. And so therefore I have to put subscripts on their charges as well. Okay. And so now, basically, what I'm going to do is I'm going to do some craziness here, and I'm going to go ahead and sub in, right, my my V2 here and my V1 here, and then my Q1 and my Q2 are going to stay. Actually, I'm going to change my Q2 into 2 times Q1, because remember, Q2 is equal to 2 times Q1. So I'm going to put that right there. So watch how this unfolds. So R2 is M V2. Remember, V2 is this. So it's actually going to be equal to the square root of 4 delta V Q1 over M over Q2, but Q2 is 2 times Q1, and B sine theta, all right? And R1 is M V1, but V1 is the root of 2 delta V Q1 over M, and then Q1 B sine theta, right? So remember what I did is I put V1 from here into there, and V2 from here into there. And then I changed Q2 to Q1, and I left this Q1 as a Q1. Why am I doing that? Because now, again, just gonna go ahead and put these over top of each other as ratios, okay? What some people might do at this point is simplify each of these, okay? And so, do we want to do that? Sure, I suppose we could maybe try and simplify this out, but honestly, I think it's going to be a fruitless endeavor, because what maybe might be your best approach would be to pull out the numbers, okay? So again, just pull out the numbers, because basically if I pull out these 3 numbers here, now looking at the rest of the formulas, this is M, this is delta VQ, this is Q1 B sine theta, here's a Q1 B sine theta, here's an M, a delta VQ, and an M, and they're all rooted. All the rest of that stuff is exactly the same. And so algebraically speaking, right, what we're going to get here is I'm going to go ahead and put R2 over R1 at this point. So R2 is this, but now remember what I'm going to do is I'm going to pull the numbers out of here. So here I've got basically a square root of 4 in the numerator, and then I've got a 2 in the denominator, okay? And if you want, you can write it like this. You've got the square root of 4 over 1, you know, and then you've got an M sitting in front. That's this M right here. And then this is multiplied by the square root of delta V Q1 over M. I just kind of separated out the number, okay? And then on the bottom, I've got a 2, and then I've got a Q1B. Oh, shoot, I messed that up. Hang on. This is supposed to be on the bottom of the numerator. Let me give myself a little bit more space. So basically this orange line here is going to come in right there, all right? So again, I've got in M a square root of 4 over 1, and then a square root of delta V Q1 over M. And then on the bottom, I've got a 2, and then I'll put in parentheses Q1 B sine theta. All right. And then I've got this line right here is going to go right there. Okay. And then I'm going to go ahead and write this. So I'm now producing this fraction. And basically I've got an m, and I've got a square root of 2 over 1, if you will. And then I've got the square root of delta v q1 over m. And then here on the bottom, I just have a q1b sine theta in parentheses. And so now you might be saying, well, why the heck did I do all of that? In the end, you didn't really need to, because you kind of just see that a lot of this stuff just ends up canceling. So I'll get green and I'll cancel this. So look, I've got an m in the numerator of the numerator, and I've got an m in the numerator of the denominator, right? So remember, I've got one large fraction here. And so if you could think about, if I take this bottom fraction and I reciprocate it and multiply it over here, I'm just going to end up with an m in the numerator and an m in the denominator, and those two m's will cancel. Okay? Then same thing, I'm going to end up with the square root of delta v q1 over m and the square root of delta v over q1 over m, one in the numerator, and this one's going to end up in the denominator. So those guys will also cancel. Okay? Boom, boom. And then if you look closely, my q1b sine theta will also cancel. And so as a result, all I'm left with is the square root of 4 over 2 over the square root of 2 over 1. Okay, so I basically said, all right, let me go with, I'll just point at it. So this numerator got written here. This denominator got written there. This numerator gets written there. And that denominator gets written there. And as a result, all this other extra stuff gets canceled. And I end up with a pretty nice little solid fraction here that I can just simplify. And this is the comparison of the first radius and the second radius, which keeps track of the fact that they entered the magnetic fields at different rates, at different velocities when they got in there. And not only that, they have different charges. And so their charges while in the magnetic field is accounted for as well. Okay, because we have to account for both the charge of the magnetic field, the charge of the particle and its velocity. But remember that its velocity is different due to the fact of its charge as well. And so I end up with this, okay? And if we look closely at this, it's the square root of 4 over 2, right? Which is, by the way, what is the square root of 4? It's just 2 over 2 over the square root of 2 over 1. And so in the end, it's actually just 1 over root 2, which is, let's see, what is that? If I multiply both by the square root of 2 and square root of 2, I end up with square root of 2 over 2. So going back, I'm going to grab these two guys. I've got R2 over R1 is the square root of 2 over 2. And so therefore, the second radius is the square root of 2 times greater than the first. All right. So that's number 6 there, or whatever number that is. Number 6. Yes. Okay. And so you can take a look at that one. I'll publish that separately, and then I'm going to actually take a look at number 5 as well. Hello? No, please tell me. Hello? Maybe the video didn't work. Hello, video.